The universe is not just expanding, it is slowly running down. Stars are fading, galaxies are quieting, and the future looks colder and darker than ever. In this video, scientists reveal why the cosmos is getting worse and worse with time. If this kind of mind-bending science fascinates you, hit like, subscribe, and turn on the bell so you do not miss the next journey into the universe. On the largest scales that can be seen, the universe stretches out as a faint and receding landscape of light. Galaxies appear as tiny points and smudges, scattered across an almost black background. Between them, space is not empty, but the matter there is spread so thin that, on average, only a few atoms drift in volumes larger than the size of stars. This vast scene does not stand still. Space itself expands. As it does, the light travelling through it stretches to longer wavelengths and lower energies, and the entire observable universe slowly cools and fades. Astronomers describe the portion of the universe that can be observed as the observable universe. It has a finite size because light travels at a finite speed, and the universe has a finite age. Light from very distant regions has only just enough time to reach present observers. Beyond that distance, there are regions that exist but remain unseen, because their light has not yet arrived and, due to continuing expansion, may never arrive. The boundary between the visible and the unreachable is sometimes called a horizon, like a line on a cosmic ocean that draws away over time. One of the clearest signals that fills this entire observable volume is a faint glow of microwave light that comes from all directions in the sky. This glow is the cosmic microwave background, the cooled remnant of light released when the universe changes from a hot, opaque plasma to a transparent gas early in its history. Today, this radiation has a temperature of just under 3 degrees above absolute zero. It is extremely uniform, but it is not perfectly smooth. Minute variations in its brightness and temperature trace the seeds of later structure, showing where matter is slightly denser or thinner on the larger scales. As space continues to expand, this background glow also changes. Its temperature slowly decreases as the universe grows, and its photons stretch to ever longer wavelengths. In each passing era, the average energy of this radiation falls, and the contrast between it and the cold darkness of space grows smaller. Over very long times, the cosmic microwave background becomes harder to detect with any realistic instrument because its photons are diluted and shifted far into the radio part of the spectrum. The universe does not stop changing. It simply changes in a direction that leads to less visible contrast and less accessible information. Galaxies at great distances also reveal the effect of this expansion. Their light is redshifted, a term that describes how spectral lines that arise from known atomic transitions appear at longer, redder wavelengths than the same lines measured in nearby sources. The greater the distance, the stronger this redshift, which indicates that the space between galaxies has stretched more by the time their light is seen. When astronomers look to very high redshifts, they see the universe as it appears when it is much younger, denser, and hotter. When they look at more modest redshifts, they see a universe that is older, more spread out, and cooler. Measurements of distant supernova, background radiation, and large-scale distributions of galaxies show that this expansion is not slowing down in a simple way. Instead, it accelerates. Something in the energy content of the universe behaves as a form of dark energy, a component that exerts a kind of negative pressure and causes expansion to speed up. The exact nature of this dark energy remains uncertain, and current research continues to test whether its strength changes over time or remains nearly constant. But its effect on the large-scale evolution of the observable universe is already strong. As the expansion accelerates, more and more distant regions pass beyond the horizon of what can ever be seen or influenced. This accelerating expansion has a direct effect on the amount of the universe that remains accessible. Light from some galaxies that are now just barely visible will, in the far future, never reach observers born long after the present era. The photons that now connect those regions cross increasing stretches of space that expand faster than they can be crossed. Over extremely long spans of time, the observable region for any single location becomes a smaller and smaller fraction of the whole. The universe as a physical whole may contain the same total content, but the part that can ever be sampled by observation or interaction shrinks. The cooling of the universe is therefore not only a matter of temperature, it is a combined effect of falling densities, stretching wavelengths, and receding horizons. Each of these processes acts slowly on human timescales, but steadily on cosmological timescales. Together they mean that, with passing time, the largest accessible region grows quieter and less informative. Background radiation carries less energy per photon. Signals from distant events are weaker and more stretched. The fraction of the universe that lies within the causal reach of any one location becomes ever more limited. In the present epoch, the observable universe still contains a rich record of its past. The cosmic microwave background preserves conditions from the first few 100,000 years. The distribution of galaxies maps structures that grow over billions of years. However, these records are not permanent features. The expansion of space continues to dilute them. If one imagines extremely distant future eras, the background glow approaches arbitrarily low temperatures. The most distant galaxies fade from view, and the large-scale pattern becomes harder to reconstruct from the thinning light that remains. The large-scale universe does not abruptly end, but its visible story becomes more difficult to read. From the perspective of the largest scales, then, the universe moves into states that are less sharply defined by bright signals and strong gradients. The horizon recedes, the average temperature falls, and information about the earliest times becomes less accessible to any given location. The universe continues to exist and to evolve, but the part of it that can be observed or influenced by any fixed region becomes smaller in practice, even as space itself grows larger in extent. In this way, the outermost region of the cosmos slowly shifts toward a more diffuse, quieter, and less revealing state. Within the observable universe, matter arranges itself on large scales into a pattern that resembles an immense web. Galaxies, groups, and clusters do not fill space uniformly. Instead, they lie along filaments and in dense knots, separated by wide, faint voids. This network, often called the cosmic web, grows out of tiny differences in density present in the early universe, amplified over time by gravity acting on dark matter and ordinary matter together. The result is a lattice of structures stretching over hundreds of millions of light years, with empty regions in between that contain very little material. At the intersections of these filaments sit galaxy clusters, the most massive gravitationally bound systems known. Each cluster holds hundreds or thousands of galaxies, along with vast amounts of hot gas and dark matter that outweigh the visible stars by large factors. Between clusters, the filaments themselves contain groups of galaxies and long threads of gas that bridge the gaps. Surrounding all of this lies the warm, hot intergalactic medium, a diffuse component of gas at temperatures of hundreds of thousands to tens of millions of degrees Celsius, filling much of the space between the denser strands. Gravity pulls matter along these filaments toward the densest nodes. Over billions of years, this process sharpens the contrast between overdense and underdense regions. Voids grow emptier as material flows out of them toward the web. Filaments become more pronounced as they gather gas and galaxies. Clusters gain mass as they accrete matter from their surroundings and merge with other clusters. However, this growth does not continue in the same way forever. As cosmic expansion accelerates, the motion of matter on the larger scales begins to feel the influence of dark energy more strongly than the mutual gravity between widely separated regions. In this regime, structures that are already gravitationally bound, such as clusters and the filaments immediately feeding them, remain intact. They continue to evolve under their own gravity, but the distances between separate large structures increase at an accelerating rate. The flow of new material from very distant regions slows and eventually stops, not because the matter vanishes, but because the expansion of space prevents further inflow. Over long times, the cosmic web becomes a pattern of isolated islands of matter rather than a continually growing network connecting ever larger domains. Within clusters and along filaments, the gas that fills intergalactic space tells a story of gradual cooling and loss of contrast. Initially, as matter falls into potential wells created by dark matter, gravitational energy converts into heat, gas shocks and compresses, reaching very high temperatures. In clusters, this intracluster medium emits in X-rays and glows as a thin, hot plasma. Over time, this gas radiates energy away. It cools through emission of light and through interactions with embedded galaxies and smaller structures. Cooling is not uniform. Some parts lose heat more quickly than others, forming denser regions that may later feed activity within galaxies. Still, on average, energy drains from the hot gas phase, and the contrast between hot and cold components declines. Observations show that a large share of all ordinary matter in the universe resides in these diffuse, warm to hot intergalactic and intracluster media. Detecting this matter requires sensitive measurements of X-ray emission, ultraviolet absorption, and distortions of background light as it passes through massive clusters. The patterns of temperature and density that appear in these studies indicate that the universe has moved beyond its most turbulent phase of large-scale structure formation. Shocks and mergers still occur, but the rate at which new, large structures assemble slows. The energy once locked in violent infall and heating is gradually radiated away into space. The dark matter backbone of the cosmic web, which does not emit or absorb light directly, also evolves. Numerical simulations that trace its behavior under gravity show that dark matter halos merge and grow early on, then eventually enter a slower phase where new mergers are rare and existing halos move mostly as stable, isolated structures within the expanding background. Once dark energy begins to dominate the expansion, halos separated by large distances effectively decouple from one another. Their internal dynamics continue, but their mutual interactions weaken. The growth of structure on the larger scales grinds to a near halt. In this picture, the cosmic web passes from a youthful stage of rapid assembly into a mature phase of slower evolution. Early times feature strong infall, frequent mergers, and high temperatures in infalling gas. Later times are marked by more settled configurations, longer dynamical timescales, and a gradual decline in the intensity of a large-scale energetic events. The web remains, but its role as a site of ongoing dramatic restructuring lessons. Energy that is once concentrated in large gradients and high-temperature shocks becomes more evenly distributed through radiation and weaker flows. For observers living during the current era, the cosmic web still offers a clear and measurable imprint on the sky. Gravitational lensing of background galaxies reveals the distribution of mass along filaments and in clusters. Surveys that map millions of galaxies trace the geometry of large-scale structure and show the transition from dense knots to broad voids. Yet these same observations, combined with models of cosmic expansion, suggest that the most active stages of web formation occur in the past. Going forward in time, the influence of dark energy grows, the infall of fresh material onto the larger structures diminishes, and the overall pattern of large-scale structures becomes more static, even as individual components continue their slower internal evolution. Seen from this level, the universe tends toward a state in which its biggest features are long established and gradually losing energy. Clusters and filaments persist as significant concentrations of mass, but they no longer draw in matter across ever greater distances. The diffuse gas that pervades them cools and changes phase, while the gravitational scaffolding that holds them together settles into a more stable arrangement. On the scale of the cosmic web, the transition is from a hotter, more dynamically active pattern to a quieter, cooler, more separated arrangement of matter, embedded in an expanding background that continues to thin and chill over time. On the scale of individual galaxies, the universe reveals another layer of gradual decline. Each galaxy is a collection of stars, gas, dust, and dark matter bound together by gravity. Moving as an island within the wider cosmic web, some galaxies take the form of thin rotating disks with spiral arms. Others appear as smooth, featureless ellipsoids. Across these forms, the ongoing birth of new stars plays a central role in shaping brightness, colour, and structure. The history of that star formation traced over cosmic time shows a universe that has already passed its most active period. Astronomers reconstruct the record of star birth by measuring light from many galaxies at different distances. Because light takes time to travel, distant galaxies are seen as they were in the past, while closer galaxies show more recent states. When these snapshots are combined, a pattern emerges. In the early universe, galaxies formed stars at a high rate, converting large amounts of cold gas into new stellar populations. This global rate of star formation, summed over all galaxies in a given volume, rises from very low values shortly after the first galaxies appear to a broad maximum several billion years after the Big Bang. After this peak, the average rate steadily declines. This history is sometimes described as a curve that climbs, flattens, and then falls. During the rising phase, gas falls into young galaxies along filaments of the cosmic web, cools, and condenses into dense clouds. These clouds collapse under their own gravity to form clusters of massive, short-lived stars and numerous smaller, long-lived stars. At the peak stage, often called cosmic noon, many galaxies are bright, blue, and clumpy, with thick gas-rich disks and frequent bursts of star formation driven by mergers and encounters. Over time, several processes work together to reduce this activity. Gas reservoirs are gradually used up as they are turned into stars. Some of the gas is locked away for very long periods in low-mass stars that burn their fuel slowly. Other gas is expelled or heated by feedback, supernova explosions, stellar winds, and radiation from massive stars push on surrounding material, stirring it, heating it, and sometimes driving it out of the galaxy entirely. In more massive systems, Energy released near central supermassive black holes can heat or eject gas from the central regions, preventing it from cooling and forming new stars. At the same time, the rate at which fresh gas arrives from outside the galaxy decreases. In the early universe, when the cosmic web is still assembling, cold gas can stream efficiently along filaments into galaxy halos. As structures mature and the space between them expands more rapidly, these inflows become less effective. Gas falling into massive halos is shock-heated to high temperatures and may remain in a hot, diffuse state for long periods, radiating energy only slowly. The balance between cooling and heating shifts, and less gas reaches the cold, dense phase where star formation occurs. Observations at many wavelengths support this picture of decline. Surveys in ultraviolet light track the presence of young, massive stars that live for only short times, so their abundance acts as a direct indicator of ongoing star formation. Infrared and submillimeter observations reveal dust warmed by these same stars and allow estimates of hidden star formation in dusty regions. Together, these datasets show that the average star formation rate per unit volume of the universe today is much lower than it is at earlier epochs, by more than an order of magnitude compared with the peak period. The appearance of galaxies changes along with this shift in activity. Gas-rich spiral galaxies with bright arms and blue light from young stars remain, but many systems move toward more quiescent states. In dense environments, where galaxy encounters and mergers are common, interactions can first trigger starbursts and then rearrange or expel gas, leaving behind spheroidal galaxies with little cold gas and predominantly older, redder stars. These quiescent galaxies still contain large stellar masses, but their current star formation rates are low. Even in galaxies that continue to form stars, the distribution of activity becomes more patchy and regulated. Massive star-forming clumps that dominate early disks become less common. Instead, star formation proceeds in more modest regions, governed by local conditions in the interstellar medium. Feedback from previous generations of stars maintains a complex balance between cooling and heating that keeps much of the gas from collapsing all at once and stretches out the remaining star formation over long time scales at a lower overall intensity than during the peak era. The influence of central black holes also becomes more apparent in regulating galactic gas. When material falls toward a supermassive black hole at a galaxy center, it can release enormous amounts of energy in the form of radiation and jets. This energy couples with the surrounding hot gas, inflating bubbles and driving outflows that reduce the supply of cold gas available for star formation in massive galaxies and clusters. This feedback helps keep large reservoirs of gas in a warm or hot state, preventing them from cooling rapidly. As a result, the galaxies remain dominated by old stars rather than experiencing renewed bursts of youth. Current theoretical models and observations suggest that the universe has already formed a large fraction of the stars it will ever create. There is still gas left in galaxies and in intergalactic space, and star formation will continue for very long times on human scales. However, the overall trend is downward. Each passing billion-year span adds fewer new stars than the one before. The cosmic inventory of bright, short-lived stars that light up galaxies and drive energetic processes gradually shrinks, while the share of mass locked in long-lived, faint stars and stellar remnants grows. On the scale of galaxies and their collective history, the universe therefore moves from a phase of vigorous construction into an era of slow finishing work. The scaffolding of dark matter halos and the flow of gas along the cosmic web build up structures early, fueling intense bursts of star formation. Later, Those same structures settle, supplies run low, and internal feedback limits further growth. Galaxies do not stop evolving, but their visible changes become more subdued. Colors redden, luminosities decline, and the rate at which new stars appear falls, marking a gradual decrease in the cosmic capacity to generate fresh starlight. The Milky Way lies as one island in the larger cosmic web, a barred spiral galaxy rotating calmly in a universe that no longer forms stars as rapidly as it once does. It sits within a modest group of galaxies, surrounded by a thin background of microwaves that has cooled for billions of years, and by intergalactic gas that carries less heat than in earlier times. In this setting, the galaxy moves through space with steady motion, not in a crowded early universe filled with frequent major collisions, but in a quieter epoch where the most violent growth has already passed. As a structure, the Milky Way shows several distinct components. A central bar of stars crosses its inner region, feeding a bright bulge packed with the old stellar populations and threaded by gas and dust. From this central zone, a thin disk spreads outward, containing spiral arms that wrap around the galaxy and carry much of its cold gas and young stars. Above and below the disk stretches a more diffuse halo of old stars and dark matter, extending far beyond the visible edge. Globular clusters orbit within this halo, and faint streams of stars mark the remnants of small galaxies that the Milky Way has absorbed in the past. Star formation in the Milky Way takes place mainly in the spiral arms of the disk. There, dense molecular clouds collapse into clusters of newborn stars, lighting up surrounding gas and sculpting it into shells and filaments. However, the overall rate at which these new stars appear is modest compared with the most active galaxies in the universe. Estimates suggest that the Milky Way converts only a few solar masses of gas into new stars each year. This rate is sufficient to sustain bright patches of star formation across the disk, yet it is far below the intense starbursts seen in galaxies earlier in cosmic history or in rare nearby systems undergoing strong interactions. The supply of gas that feeds this activity is finite and distributed in several phases. A cold, dense component in the disk provides the immediate raw material for star birth. Warmer atomic gas surrounds and threads through these denser regions. Beyond the disk, a large halo of very diffuse hot gas envelopes the galaxy, extending for hundreds of thousands of light years. This halo plays a role as a reservoir and as an interface with the surrounding intergalactic medium. Gas may slowly cool and rain down onto the disk, while outflows from supernova and stellar winds push gas back into the halo. The net result is a gradual cycling of matter, but one in which the balance does not favour an endless increase in star formation. Evidence from stellar populations suggests that the Milky Way forms stars more slowly now than in its past. The disk contains stars of many ages, but there is a significant population of intermediate age and old stars that trace periods when the galaxy is more gas-rich and more active. The chemical composition of stars, expressed through the relative abundance of elements heavier than helium, records the build-up of these elements through previous generations of massive stars and supernovae. Patterns in these abundances across the disk and halo indicate that the Milky Way experiences earlier phases of higher star formation, followed by a long decline toward the present level. The galaxy's environment reinforces this picture of a system in a calmer cosmic era. The Milky Way belongs to the local group, a small assembly of galaxies dominated by two large spirals and numerous dwarf companions. Gravitational interactions within this group are gentle on short timescales, involving slow orbital motions and the gradual stripping of gas and stars from small satellites. The space between the large galaxies is filled with a sparse medium that has cooled along with the universe. Major mergers are rare events in the current epoch, and while distant future encounters are inevitable, the present structure of the Milky Way reflects a period of relative dynamical quiet compared with the chaotic assembly phase earlier in its history. Within the disk, the spiral arms themselves show the imprint of a galaxy that is neither newly formed nor exhausted. They contain clusters of hot blue stars that live only briefly, marking recent star formation. But these clusters sit within a broader background of older, redder stars that dominate the mass and provide most of the light. Interarm regions are not void. They hold a diffuse distribution of stars and gas that has already passed through previous cycles of formation and feedback. The contrast between arm and interarm, and between inner and outer disk, is strong enough to define a clear pattern, yet it does not signal a galaxy in the midst of a violent starburst. The central regions of the Milky Way also show signs of a maturing system. The bulge hosts a dense mix of stars with a wide range of ages but with a bias toward older populations. Nestled at the very center lies a supermassive black hole that affects its surroundings through gravity and, at certain times, through bursts of energy released as gas falls inward. At present, this central engine is relatively subdued, indicating a low rate of gas accretion compared with more active galactic nuclei seen elsewhere. The calm state of the central regions aligns with the moderate global star formation rate, and with a general absence of large new inflows of gas. Farther out, in the stellar halo, long, faint streams of stars stretch across the sky, remnants of dwarf galaxies that are torn apart by the Milky Way's gravity. These features act as records of past growth, showing that the galaxy has built up its mass through the gradual accretion of smaller systems. Many of these events occur long ago, when the universe is denser and interactions more common. Today, some satellites continue to fall inward, but the overall pace of such accretion is slower. The halo stars are typically old and metal-poor, reflecting an earlier, less enriched epoch of star formation, and their continued dominance in the outer regions further emphasizes how much of the galaxy's assembly lies in the past. One ordinary star among the hundreds of billions in the Milky Way is the Sun, orbiting in the disk at a distance of tens of thousands of light-years from the center. Around it, a planetary system circles within one of the spiral arms. This location places it inside a galaxy that is no longer in its vigorous youth, but not yet in a completely quiescent old age. The surrounding interstellar medium still forms new stars, yet many nearby stars are already old, and the general properties of the disk point toward a long period of steady, moderate activity rather than rapid growth. Taken together, these aspects present the Milky Way as a galaxy living in a colder, more settled universe than the one that exists during cosmic noon. The background radiation that bathes it has cooled. The intergalactic medium around it holds less available thermal energy, and the main episodes of violent assembly and intense star formation lie in the past. The galaxy continues to rotate, to form stars, and to exchange gas with its surroundings. But it does so within an environment defined by declining global star formation and a slow drift toward lower contrasts in temperature and activity. In this way, the Milky Way serves as a clear example of how a typical large galaxy behaves in the present, more subdued stage of cosmic evolution. Within the Milky Way, the space between stars is filled with gas, dust, magnetic fields, and energetic particles that together form the interstellar medium. This medium is not uniform. Some regions are hot and very diffuse, others are warm and moderate, and still others are cold and dense enough for molecules to form. These components blend into one another, stirred by gravity, radiation, and explosions, and they create a changing environment from which new stars arise. Over long spans of time, the overall character of this medium shifts as the galaxy's energy input declines and its gas becomes less ready to collapse. The hot phase occupies large volumes in and above the galactic disk. It consists of gas heated to millions of degrees Celsius by supernova explosions and fast stellar winds. When massive stars end their lives and explode, their shock waves carve out bubbles and cavities, pushing aside cooler gas and filling these regions with high-temperature plasma. This hot gas glows in X-rays and can rise into the galactic halo before gradually cooling and mixing with surrounding material. In the present epoch, the Milky Way forms stars at a moderate rate, so the supply of new supernovae is steady but not extreme. The hot phase is extensive but patchy, threaded with cavities and chimneys that connect the disk to the halo. In earlier stages of the galaxy's life, when star formation is more vigorous, the combined effect of many massive stars produces larger, more energetic superbubbles and stronger galactic fountains of hot gas. With lower star formation today, fewer such structures reach extreme sizes, and the average heating of the interstellar medium is comparatively subdued. More common in mass, though not always in volume, is the warm phase. This gas sits at temperatures of thousands to tens of thousands of degrees Celsius and occupies much of the interstellar space within the disk. It is partly ionized by ultraviolet radiation from young stars and by shocks and cosmic rays. The warm interstellar medium outlines spiral arms and large shells, flowing around denser clouds and filling in the gaps between them. Within this warm background lie colder, denser clouds of atomic gas and, deeper inside, molecular clouds. These structures make up the cold phase of the interstellar medium, with temperatures of only tens of degrees above absolute zero and densities high enough for hydrogen to exist mainly in molecular form. Dust grains mixed into the gas help shield molecules from destructive radiation and allow them to cool efficiently. In the darkest, coldest cores of these clouds, gravity can overcome internal pressure and turbulence, leading to collapse and the formation of new stars. These regions glow faintly in infrared and radio wavelengths. The balance between these phases arises from the competition between heating and cooling processes. Supernovae, stellar radiation, and cosmic rays heat the gas. Radiative cooling, expansion, and mixing with other phases allow it to lose energy. The distribution of energy injection sources determines how turbulent and clumpy the medium becomes. When energy input is high, as in earlier epochs of more intense star formation, the interstellar medium is strongly stirred. Shocks and waves propagate widely, fragmenting clouds and creating many dense pockets where stars can form. As the rate of supernovae and strong stellar winds diminishes, the level of turbulence drops, and the medium becomes more settled on average. Observations of gas and dust in the Milky Way show that much of the cold molecular gas resides in large complexes that convert only a small fraction of their mass into stars over their lifetimes. Star formation in these clouds appears inefficient and regulated. Feedback from newly formed stars disrupts the surrounding gas, halting further collapse in some regions and dispersing material into the wider medium. This feedback is sufficient to prevent the entire cloud from collapsing rapidly, but not so strong as to reheat all the gas to hot phase temperatures. The result is a slow, steady consumption of gas rather than a rapid burst. Dust grains act as both participants and tracers of these processes. They absorb starlight, especially at ultraviolet and visible wavelengths, and re-radiate the energy in the infrared. The temperature of dust reflects the intensity of the surrounding radiation field. Measurements across the sky indicate that the average dust temperature in the Milky Way is consistent with a galaxy in a moderate, not extreme, star-forming state. In comparison with more active galaxies, the dust is cooler, and the contrast between the brightest star-forming regions and the diffuse background is less stark. Magnetic fields and cosmic rays add further structure to the interstellar medium. Magnetic fields guide the motion of charged particles, help support gas against gravity, and shape filaments and sheets seen in radio and submillimeter maps. They are maintained by dynamo processes that rely on the galaxy's rotation and on turbulent motion in the gas. Cosmic rays, which are high-energy particles mostly accelerated in supernova remnants, permeate the galaxy and contribute to ionization and heating even in regions shielded from direct starlight. As star formation and supernova activity decline, the inputs that drive turbulence, magnetic amplification, and cosmic ray production diminish in step. Taken together, these factors describe an interstellar medium that is still alive with motion but gradually quieter than in the galaxy's youth. Gas continues to cycle between phases, clouds still collapse, and stars still form. Yet the intensity of each process is reduced compared with earlier epochs. The hot cavities carved by supernovae are less numerous and less violent on average. The warm gas flows more gently. Cold molecular clouds form fewer massive clusters and more modest groups. Dust, magnetic fields, and cosmic rays still carry energy, but across a backdrop of decreasing turbulence and slowly dwindling energy injection. From this perspective, the interstellar spaces within the Milky Way are part of a broader cosmic pattern. As the global rate of star formation declines, the environments that give rise to stars become more subdued. The medium between the stars does not freeze or stop evolving, but it shifts towards states where contrasts in temperature, density, and motion are less extreme. Over long spans of time, energy spreads out, gradients soften, and the galaxy's gas reservoir grows calmer, even as it continues to serve as the cradle for the remaining generations of stars that the Milky Way will produce. Stars fill galaxies as the basic units of visible light, countless points that together trace disks, bulges, and halos. Each star is a sphere of hot gas held in balance by gravity pulling inward and pressure pushing outward. In its long stable phase, called the main sequence, a star shines by fusing hydrogen into helium in its core. The details of this fusion and the path a star follows after its fuel begins to run low depend mainly on the star's mass. Across cosmic time, the mix of stellar masses and ages in a galaxy gradually shifts, and this shift changes the overall character of its light and its energy output. Massive stars, with several times the mass of the Sun or more, burn their fuel quickly. Their central temperatures and pressures are high, and fusion proceeds at a rapid rate. These stars shine with intense luminosity and appear blue or white. However, their lifetimes on the main sequence are short on cosmological scales, lasting only a few million to tens of millions of years. When their cores exhaust hydrogen, they pass through brief later stages of fusion, forming heavier elements up to iron before ending their lives in core collapse supernova, leaving behind neutron stars or black holes. Stars of intermediate mass, similar to or somewhat larger than the Sun, burn their fuel more slowly. Their main sequence lifetimes span billions of years. These stars appear yellow or white, As hydrogen runs out in the core, they expand into red giants, their outer layers cooling and their radii increasing. In these phases, they shed mass through stellar winds, enriching their surroundings with elements formed during their lives. Their final remnants are white dwarfs, compact objects with masses comparable to the original star's core, supported against gravity by electron degeneracy pressure and slowly cooling over immense timescales. Low-mass stars, with less than about half the mass of the Sun, follow even slower paths. Their cores are cooler and their fusion rates lower. They shine with relatively low luminosity and appear red. Their main sequence lifetimes can exceed the current age of the universe by large factors. This means that nearly all low-mass stars that have ever formed are still on the main sequence today. They continue to fuse hydrogen steadily, losing mass only gently through stellar winds, and have not yet entered the advanced phases of evolution that will eventually turn them into white dwarfs. The initial mass function, a statistical distribution that describes how many stars form at each mass in a typical episode of star formation, favors low-mass stars. For every massive star that forms, many more stars of low and intermediate mass appear. Early in a galaxy's history, when star formation rates are high, massive stars are numerous enough to dominate the ultraviolet and blue light, and their supernova explosions drive strong feedback. Yet even then, the majority of stellar mass accumulates in lower mass stars that live far longer than the massive ones. As time passes and the most massive stars die, the visible population shifts toward these longer-lived, less luminous sources in the present universe. Many galaxies, including the Milky Way, already host stellar populations in which most of the massive stars born in earlier epochs have ended their lives. Their remnants remain as neutron stars and black holes, often hard to detect directly except when gas or a companion star supplies matter that can radiate as it falls inward. White dwarfs, the common endpoints of intermediate mass stars, populate the stellar neighborhood in large numbers, glowing with residual heat and fading slowly. These remnants represent a shift in where matter and energy reside. The luminous phases of massive and intermediate mass stars are transient compared with the long cooling times of white dwarfs or the essentially indefinite existence of neutron stars and black holes. Over time, more and more of a galaxy's stellar mass becomes locked in these compact faint objects. Their contribution to visible light dwindles as they cool and as accretion events become less frequent. Meanwhile, low-mass main sequence stars continue to shine steadily but modestly, carrying the remaining active fusion in their cores at a slow pace. The overall spectrum of a galaxy reflects this changing mix. Young stellar populations dominated by massive blue stars emit strongly at short wavelengths, making galaxies appear blue and highly luminous. As those massive stars die and the proportion of older, cooler stars increases, the light shifts toward longer wavelengths. Galaxies move along a sequence in which their colors redden and their brightness per unit mass declines. This trend is marked in galaxies that have already quenched most of their star formation. Their spectra show the signatures of old stars and only weak indicators of ongoing formation of hot, massive stars. On larger scales, the changing stellar population alters how energy is injected into the interstellar medium. Supernova rates track the death of massive stars and so decrease as fewer such stars are formed. The supply of ionizing ultraviolet radiation, which comes mainly from very luminous young stars, also falls. As a result, the heating and stirring of interstellar gas by stars declines. The medium still receives energy from older stars through gentle winds and planetary nebula ejection. but these are weaker drivers of turbulence than the explosions of high-mass stars. From a long-term perspective, the universe enters an era in which the active, short-lived phases of stellar evolution become less common, while the long-lived, slowly changing phases dominate. The balance shifts from bright, hot, brief episodes of fusion toward extended periods of faint, steady burning, and the quiet presence of degenerate remnants. The number of new massive stars formed per unit time declines with the overall star formation rate, while the number of white dwarfs, neutron stars, and black holes accumulates with no corresponding process that turns them back into diffuse gas on similar timescales. Thus, on the level of individual stars and their collective behavior, the universe moves from a state rich in bright, short-lived sources to one where long-lived, low-luminosity stars and compact remnants hold most of the mass. The energy output per unit mass decreases, the colors shift toward redder tones, and the frequency of powerful stellar explosions and intense radiation episodes falls. Stars still trace the structures of galaxies, but the character of their light and their impact on surrounding gas reflect a cosmos that has already spent much of its easily accessible stellar fuel, and now progresses through stages of more restrained, slowly fading luminosity. Planetary systems arise in the disks of gas and dust that surround young stars. In the early stages of star formation, a collapsing cloud of molecular gas flattens into a rotating disk as angular momentum is conserved. Within this disk, tiny solid particles collide and stick, gradually growing from dust grains to pebbles, then to larger planetesimals tens to hundreds of kilometers across. Some of these bodies continue to accumulate mass through further collisions and gravitational focusing, becoming planetary embryos and eventually full-size planets. At the same time, gas in the disk interacts with forming bodies, altering their orbits and redistributing angular momentum. In the dense, gas-rich disks of the early universe, when star formation is more intense, this process occurs frequently. Many stars host substantial protoplanetary disks with enough material to build multiple planets and extensive belts of smaller debris. Observations of young stellar clusters show numerous disks glowing in infrared light, evidence of warm dust grains heated by their central stars. Over a few million years, these disks evolve. Gas is lost through accretion onto the star, photoevaporation, and the formation of giant planets that capture large gas envelopes. Dust is ground down in collisions and grows into larger bodies that no longer contribute strongly to the infrared glow. As protoplanetary disks disperse, planetary systems settle into gravitationally bound configurations of planets, remaining debris and smaller bodies such as asteroids and comets. However, this settling is not a simple, smooth process. Planets migrate through the disk while gas remains, moving inward or outward depending on their mass and on local disk properties. Even after the gas is gone, mutual gravitational interactions between planets can rearrange orbits. Close encounters scatter planets onto more eccentric paths, or even eject them entirely from the system into interstellar space. Smaller bodies are perturbed into new trajectories, some falling toward the star, others flung into distant reservoirs or out of the system altogether. Over time, these interactions lead to a gradual clearing and thinning of planetary systems. In the early chaotic phase, collisions between embryos and planetesimals are common, building larger planets, but also producing fragments and dust. As time passes, the number of large bodies on crossing orbits declines. Stable configurations emerge in which surviving planets occupy orbits that avoid close encounters. Leftover debris is either incorporated into planets, ground down in collisional cascades that produce fine dust, or removed by radiation forces and gravitational scattering. What remains is a smaller population of planets and minor bodies moving on longer-lived, more regular paths. The long-term evolution of a planetary system continues beyond this initial clearing. Planets exchange angular momentum with one another through resonances, subtle, repeated gravitational tugs that can alter eccentricities and inclinations over tens of millions or billions of years. Interactions with belts of smaller bodies, such as asteroid belts or distant icy reservoirs, can slowly shift orbital elements. Tidal forces between close-in planets and their host stars can circularize orbits and cause gradual inward drift. Stellar mass loss during later phases of stellar evolution can also expand planetary orbits, changing the architecture of the system. As the universe ages and star formation declines, new planetary systems still form around young stars, but the overall rate at which fresh systems appear decreases. The gas reservoirs feeding star formation are less abundant and less dense on average, and the resulting disks may in some environments be less massive than those in earlier cosmic epochs. Even in similar disks, the background environment changes. High-energy radiation fields, nearby massive stars, and frequent close stellar encounters are more common in dense, active regions of the early universe. In later times, more stars form in comparatively sparse regions where external perturbations to disks are milder, leading to fewer dramatic truncations and disruptions, but also to a quieter dynamical environment. Across cosmic time, the cumulative effect is a growing population of planetary systems that have moved beyond their formative turbulence. The orbits of many planets have already been reshaped by migration and scattering. Systems that remain intact tend to occupy configurations that are dynamically stable over long spans. Evidence from observed exoplanetary systems shows a wide variety of architectures, including tightly packed inner systems, widely separated giants, and solitary planets with distant companions. The diversity reflects the multitude of possible pathways through the early chaotic phase, but the common feature is that present observations usually capture systems that have already survived major instabilities. In mature systems, debris disks persist as faint belts of dust and small bodies, illuminated by the central star and detectable at infrared and sub-millimeter wavelengths. These belts trace the remnants of larger populations of planetesimals that are now gradually eroding through mutual collisions. Each collision grinds bodies into smaller fragments, which then collide again, creating a cascade down to fine dust grains, eventually removed by radiation pressure and stellar winds. The dust production rate declines as the reservoir of larger bodies shrinks. Old debris disks therefore appear fainter and less massive than young ones, signaling a steady decrease in the amount of solid material still participating in active collisional evolution. Some planets do not remain bound. Gravitational interactions can expel them from their systems, sending them into interstellar space as free-floating planets. Surveys suggest that such objects exist in significant numbers, although their exact abundance remains uncertain because they are difficult to detect. These planets carry with them their internal heat and any remaining atmospheres, but without a nearby star, their external environment is dark and cold. They drift through the galaxy, participating only weakly in further dynamical evolution unless they pass close to other stars or encounter dense molecular clouds. Thus, on the scale of planetary systems, the passage of time leads from dense, gas-rich disks full of colliding building blocks to more diffuse arrangements of settled orbits and depleted debris. The most violent stages of planet building occur early and then give way to long periods of slower change, during which orbits adjust gradually and the inventory of small bodies declines. The universe still hosts many systems in varied states of evolution, but the general trend follows the broader cosmic pattern from an initial phase rich in structure formation and energetic interactions toward a later era, characterized by more stable configurations, lower collision rates, and a thinner distribution of material around stars. Around each star there exists a region where temperatures on the surface of an Earth-like planet could allow liquid water to persist for long periods. This region is often called the habitable zone. Its location depends mainly on the star's luminosity and on how efficiently a planet's atmosphere traps heat and reflects light. At a given moment there is a band of distances within which incoming energy from the star balances with the planet's ability to radiate energy away, so that surface temperatures can remain moderate rather than freezing solid or driving off all surface water. Because stars evolve, the extent and position of their habitable zones change with time. As a star fuses hydrogen into helium in its core, its internal structure slowly adjusts and its luminosity does not stay constant. For a star like the Sun, the main sequence phase lasts for billions of years, during which its luminosity increases. Early in this phase, the star is dimmer, and the region where surface liquid water is stable lies closer in. As the star brightens, the habitable zone moves outward. A planet that begins comfortably within this moving band can find itself receiving gradually more energy, drifting toward the inner edge where oceans become harder to maintain. Lower mass stars evolve more slowly and change their luminosity more gently. Their habitable zones lie close to the stellar surface and move on very long timescales. In principle, this offers extended intervals during which a planet at a fixed orbit can remain within temperate conditions. At the same time, the close distance makes planets more susceptible to tidal locking, with one hemisphere facing the star continuously and the other in darkness. The resulting day-night contrast means that stable climates depend strongly on how well atmospheres and any oceans transport heat between hemispheres. More massive stars burn brighter and live shorter lives. Their habitable zones lie farther out but move rapidly as the stellar luminosity rises and later falls. For these stars, the span of time during which a planet at a fixed orbit remains within the habitable band is often short compared with geological and biological timescales. Even if solid planets assemble at suitable distances, the quickly changing radiative environment means that any period of temperate surface conditions is brief. Orbital dynamics add further variation. Planetary orbits respond to mutual gravitational tugs and to the influence of belts of smaller bodies. Over long periods, these interactions alter orbital distances and eccentricities. In some systems, orbits remain nearly circular for extended times, keeping planets at almost constant distances from their stars. In others, orbital eccentricities grow, so that planets follow elongated paths that carry them alternately closer to and farther from the star. These variations change the average and peak stellar energy received, effectively moving planets in and out of conditions associated with the habitable zone, even when the star's luminosity is steady. Tidal forces between planets and their stars also reshape orbits. For planets that circle very close in, tides raised on both bodies dissipate energy and can cause orbits to contract over time. This inward drift may carry a planet from outside the habitable zone into it, or from within it to hotter regions where surface water would be unstable. In other situations, tides mainly circularize orbits, reducing extreme temperature swings but locking the planet more firmly at a given distance and, for close-in worlds, synchronizing rotation. Stellar mass loss introduces another slow adjustment. As stars age, they shed mass through stellar winds. When a star loses mass, its gravitational pull on its planets weakens and their orbits expand. Planets can drift outward while the star becomes more luminous, so the location of the habitable zone shifts in ways that do not simply track distance. In many cases, the rise in luminosity dominates, and surface conditions still move beyond the range compatible with long-term surface oceans. Taken together, these processes mean that habitable zones are best thought of as moving, deforming bands rather than fixed shells. For any given planet, the interval of time spent within such a band depends on its initial orbit, on the later dynamical evolution of the system, and on the pace of stellar evolution. In many configurations, the span of continuous temperate conditions is limited. A planet may begin too cold, later pass through a favorable zone, and eventually emerge into hotter or colder states as its star and orbit change. In systems with significant eccentricity, this passage can occur in cycles, with alternating periods of relative stability and instability in surface conditions. On the scale of the universe as a whole, these individual histories unfold within a changing stellar population. Early in cosmic history, when star formation is vigorous, massive stars are more common among the luminous sources. Their short lifetimes and rapidly evolving habitable zones offer only brief opportunities for planets to experience steady, moderate surface conditions. As time passes and the formation of new massive stars declines, the average population shifts toward lower mass stars with longer main sequence lifetimes. At the same time, the overall rate at which new stars and planetary systems appear decreases. Fewer fresh systems enter the early stages of their evolution, and more systems move into phases where their stars have altered luminosities or where orbital dynamics have already reshaped the initial architectures. In later cosmic epochs, many planets around Sun-like and more massive stars will have already passed through their most stable habitable periods. Around lower mass stars, habitable zones endure for very long times, but their close-in locations, strong magnetic and flare activity in early phases, and the likelihood of tidal locking create conditions where the maintenance of temperate surfaces depends on balances that can shift over time. Thus, the concept of a habitable zone emphasizes that surface-friendly environments are transient in a universe where both stars and orbits evolve. Planets occupy spaces defined by distance and by time, moving through bands of suitable conditions that shift with stellar brightness and respond to slow dynamical changes. Across all galaxies, the total number of planets that ever pass through such zones may be large. Yet for each world, the duration of this passage is finite. In a cosmos where star formation is already in decline and stellar populations are aging, the long-term trend favors systems in which the broadest, most stable windows for surface habitability gradually narrow. While many planets move onward into states less able to sustain liquid water on their surfaces, rocky planets begin their histories as hot, partially or fully molten bodies. During their formation, countless collisions between growing planetesimals convert kinetic energy into heat. Radioactive elements concentrated in their interiors provide additional heat as they decay. For many young planets, these processes melt large portions of their mantles, creating global or regional magma oceans. At the surface, this molten rock radiates energy into space, cools, and solidifies into a crust. In the earlier stages, surfaces are unstable, with frequent volcanic outpourings, heavy impact cratering, and rapid recycling of the outermost layers. As time passes, the rate of large impacts decreases. The planet clears its orbit of most big debris, and only smaller impactors arrive. Internal heat, however, remains high. Convection in the mantle, the slow, churning motion of solid but deformable rock, transports heat from the deep interior toward the surface. On some planets, this convection couples with a mobile outer shell of rigid plates that move, collide, and slide past each other in plate tectonics. On others, the outer shell remains largely intact as a single lid, with convection confined beneath it. The style of this mantle flow shapes the surface, determining whether mountains rise mainly along plate boundaries or whether broad volcanic provinces develop in more static patterns. Volcanism acts as a main pathway for interior heat to reach the surface. Rising plumes of hot mantle material partially melt as pressure drops, feeding magma chambers and volcanic vents. Lava flows spread across the surface, forming plains, building volcanoes, and covering older terrains. Where plate tectonics operates, volcanism often concentrates along spreading ridges and subduction zones, renewing ocean basins and adding material to continental areas. Where a stagnant lid dominates, volcanism may occur above mantle plumes that punch through the overlying shell, generating isolated volcanic constructs or widespread flood basalts. In both regimes, volcanic activity is most intense when the internal heat budget is high and mantle convection is vigorous. Over geological timescales, internal heat sources diminish. Radioactive isotopes with short half-lives release much of their energy early, while those with longer half-lives provide a slowly declining background. Heat left over from formation leaks away through the surface. As the total internal heat content falls, mantle convection slows, and the rate of volcanism decreases. The crust thickens in places, and the capacity of the lithosphere to deform changes. On worlds where plate tectonics once operates, the forces that drive plate motions may weaken, altering or halting the cycle of subduction and creation of new crust. On worlds with a stagnant lid, volcanism may shift from widespread flows to more sporadic, localized events. The cooling interior also affects planetary cores. In many rocky planets, a metallic core, primarily iron and nickel, sits beneath the silicate mantle. If the core is hot and convex, and if it contains both liquid and solid regions, it can sustain a magnetic dynamo. This dynamo generates a global magnetic field that extends into space, deflecting charged particles and shaping the near-planetary environment. The strength and longevity of this field depend on the rate at which heat and light elements are removed from the core into the mantle. As the planet cools, core convection can change or diminish. In some cases, the core begins fully liquid and cools until solidification starts at the center or at the top, releasing latent heat and driving compositional convection. This phase can enhance the dynamo for a time. Eventually, as more of the core solidifies and heat flow across the core mantle boundary drops, convection wanes and the magnetic field weakens or disappears. In other cases, the core may cool quickly enough or be small enough that it never supports a long-lived, strong field. Surface geology records this interior evolution. Heavily cratered highlands mark periods when impacts are frequent and resurfacing is less effective at wiping away scars. Smooth plains and extensive lava flows indicate episodes of high volcanic output. Mountain ranges, rift valleys, and folded belts show where the lithosphere has deformed under compression or extension. On a planet with active plate tectonics, old oceanic crust is recycled into the mantle and replaced by new basalt at spreading centers, so the surface crust has a limited maximum age. Continental regions preserve longer records, but even these are modified by uplift, erosion, and metamorphism. On planets without sustained plate tectonics, old terrains can survive for billions of years, with only limited resurfacing events superimposed on them. On many rocky worlds in the current universe, the most active phases of interior and surface reshaping lie in the past. The large terrestrial planets in the solar system illustrate different stages. Some show thick volcanic plains and few young tectonic features, implying that vigorous activity has largely ceased. Others retain plate tectonics and widespread volcanism, but at lower rates than in earlier epochs. Smaller bodies cool more quickly because their surface area to volume ratios are higher. Their interiors lose heat faster, and their capacity to sustain long-term convection and magnetic fields is limited. As a result, many small rocky bodies become geologically inactive relatively early, preserving ancient cratered surfaces. Across galaxies, newly formed rocky planets still pass through molten stages and early intense volcanism. However, the declining rate of star and planet formation means that the average rocky planet in existence at a given time is older as the universe ages. Older planets have had more time to lose internal heat, thicken their lithospheres, and move from active to quieter tectonic and volcanic regimes. The fraction of rocky worlds that retain vigorous mantle convection, strong magnetic dynamos, and frequent resurfacing events decreases over cosmic time, while the fraction that hosts thick, stagnant outer shells and largely fossilized landscapes increases. Thus, the evolution of planetary surfaces and interiors follows a path from initial heat and fluidity toward gradual cooling and rigidity. Early molten states give way to solid crusts shaped by volcanism and tectonics. These processes then slow as internal heat sources fade. Mountains erode, large lava plains cool and crack, and impact craters accumulate without being fully erased. In the long view, rocky planets shift from dynamic, internally driven reshaping to a quieter condition in which changes at the surface proceed mainly through slow external processes, overlaying an interior that continues to cool and solidify with time. Planetary atmospheres form and evolve as gases gather around solid or liquid surfaces under gravity. At the start of a planet's history, gases arrive from the surrounding nebula, from volcanic outgassing, from impact delivery, and from chemical reactions on and beneath the surface. Once present, an atmosphere becomes a layer where radiation, convection, and chemistry interact, setting climate and mediating the exchange of energy between space, air, and ground. The composition and thickness of an atmosphere depend on the planet's mass, temperature, distance from its star, and history of impacts and internal activity. Massive planets with strong gravity and low temperatures can retain light gases such as hydrogen and helium. Smaller, hotter planets lose these gases more easily to space through thermal escape and through non-thermal processes driven by stellar radiation and particle flows. For terrestrial planets, atmospheres often end up dominated by heavier molecules such as nitrogen, carbon dioxide, and water vapor, with trace gases that strongly influence radiation and climate. Over time, atmospheres do not remain in simple equilibrium. Stellar radiation gradually changes as stars brighten or dim, and as their ultraviolet and X-ray output evolves. High-energy photons ionize and heat upper layers, contributing to escape. Stellar winds and magnetic activity interact with planetary magnetic fields, if present, and with ionized upper atmospheres, sometimes stripping material away. In the early lives of stars, when high-energy emission and flaring are strong, these processes can remove significant amounts of gas, especially from planets that lie close to their stars or that lack substantial magnetic shielding. Lower in the atmosphere, visible and infrared radiation shapes temperature, structure, and circulation. Greenhouse gases absorb outgoing infrared radiation emitted by the surface and lower air, trapping heat and elevating surface temperatures. Clouds and aerosols scatter and reflect incoming sunlight, altering the amount that reaches the ground and influencing cooling to space. The balance between incoming and outgoing energy sets the mean climate state, while spatial and seasonal variations create winds, storms, and longer-term patterns. This balance is not fixed, because the abundance of greenhouse gases and the properties of clouds and aerosols change as atmospheres age. Sources and sinks of greenhouse gases are tied to internal planetary processes and external forcing. Volcanic eruptions inject carbon dioxide, water vapor, and sulfur-bearing gases into the air. Weathering of rocks consumes carbon dioxide over long timescales, transferring carbon into solid and dissolved forms. Photochemical reactions in the upper atmosphere create and destroy molecules. As internal heat flow decreases and volcanism wanes, the rate at which fresh gases are delivered from the interior declines, over very long periods. This reduction in outgassing allows surface and near-surface processes to draw down certain atmospheric components faster than they are replenished. Atmospheric escape continues as a slow loss mechanism. Thermal escape removes light gases when energetic particles in the high atmosphere reach speeds exceeding the planet's escape velocity. Non-thermal escape, such as sputtering by energetic particles and ion pickup, can remove heavier species, especially where magnetic shielding is weak or absent. As stars age and their high-energy output decreases, some of these loss rates decline, but the cumulative effect over billions of years still alters atmospheric mass and composition, particularly for smaller planets. On many worlds, the long-term trend is toward atmospheres that either become thinner and less able to support complex weather, or thicker and more stably stratified with reduced gradients. On smaller rocky planets close to their stars, persistent escape and reduced volcanic supply thin the atmosphere, leaving behind only a tenuous layer or none at all. Temperature contrasts between day and night or between equator and pole may still exist, but the capacity of air to transport heat and moisture is limited, and surface conditions are controlled more directly by radiation and conduction. On larger terrestrial planets, with substantial gravity and early outgassing, atmospheres can instead grow dense. Over time, greenhouse gases accumulate if they are not efficiently removed, and feedbacks may occur in which warming increases greenhouse gas abundance. When interior heat decreases and volcanism subsides, the input of new gases weakens. Weathering and other sinks then proceed until a new, often hotter and more stable equilibrium emerges, with thick, slow-moving envelopes that support less vigorous circulation than earlier. More dynamic stages, gas giant planets and ice giants present related patterns. Their deep hydrogen-rich atmospheres remain bound despite continuous escape from upper layers. Internal heat and slow contraction provide ongoing energy, driving convection and weather systems. As these planets radiate away residual formation heat, their atmospheres cool and circulation patterns adjust. Zonal winds and storms persist, but may weaken over immense timescales as thermal gradients decline, and contrasts between active bands and calmer regions lessen. Chemistry within atmospheres also ages. Photochemical pathways depend on the spectrum and intensity of stellar radiation and on the availability of parent molecules. In young systems, strong ultraviolet flux drives vigorous production and destruction of reactive species, maintaining complex high-altitude hazes. As stellar activity diminishes and atmospheric compositions change, some of these cycles slow or halt, haze layers can thin, and the variety of photochemical products can decrease. The net effect is a move towards simpler chemical steady states, with fewer strong gradients of composition and temperature. Across cosmic time, the declining rate of star and planet formation means that a growing fraction of planets host atmospheres that have already passed through their most changeable phases. Young, violently evolving atmospheres still exist around newly formed planets, but the average atmosphere is older, having experienced billions of years of escape, outgassing, cooling, and chemical adjustment. External drivers such as high-energy stellar emission are weaker on average than in the early universe. Internal drivers such as volcanism and core convection have diminished on many worlds as their interiors cool. From the viewpoint of atmospheric physics, the long arc of evolution on a typical planet leads towards states with lower energy throughput and reduced variability. Thick, slowly circulating envelopes or thin, nearly absent atmospheres replace intermediate configurations rich in storms, strong jets, and rapid chemical cycling. The skies above many worlds may still display clouds, winds, and seasonal changes, but on a statistical level. The universe shifts from a collection of planets with vigorously mixed, chemically active atmospheres toward one in which more planets possess air that changes only slowly, with smaller contrasts and a narrower range of dynamic behavior than in their earlier, more active epochs. On planets that host liquid water, oceans cover surfaces and fill basins, forming layers of fluid that move, mix, and exchange energy with air above and rock below. These oceans act as reservoirs of heat and chemicals, moderating climate and supporting physical and biological processes. Beneath their surfaces, light fades with depth, and conditions shifts from warm, sunlit upper layers to cold, high-pressure environments on the deep floor. Within and below these waters, life can exist as long as sufficient energy and nutrients flow through the system, drawing on heat from the star, the planet's interior, or both. In a young planetary ocean, internal heat flux and external radiation are often higher than in later times. Vigorous volcanism and tidal heating pump energy into the crust and create numerous hydrothermal systems on the ocean floor. In these systems, water circulates through fractured rock, heats up, reacts chemically with minerals, and returns to the ocean carrying dissolved substances and reduced species. When these fluids mix with colder, more oxidized seawater, gradients in temperature and chemical potential arise. Microorganisms can exploit these gradients, extracting energy by catalyzing reactions between reduced and oxidized components. At the same time, in the upper ocean, sunlight penetrates the surface layers and fuels photosynthesis. In clear water, light may reach tens to hundreds of meters below the surface, creating a photic zone where primary producers convert simple molecules into organic matter. This production supports food webs that extend into deeper layers, as sinking particles carry energy and materials downward. Circulation patterns such as overturning currents and upwelling bring nutrient-rich deep water back toward the surface, closing cycles that redistribute essential elements. As a planet ages, several drivers of ocean behavior evolve. Stellar luminosity slowly changes, altering the balance between absorbed radiation and emitted thermal energy. Internal heat flow from radioactive decay and residual formation energy decreases, reducing the intensity and extent of hydrothermal activity on the seafloor. Tidal heating may weaken as orbits circularize and rotation rates adjust. The atmosphere above the ocean also changes, influencing the winds that drive surface currents and waves. Together, these trends reshape the vertical and horizontal structure of the ocean over long time scales. A declining internal heat flux leads to fewer and less vigorous hydrothermal vents. The length of active spreading ridges and the number of large volcanic centers on the seafloor may diminish as mantle convection slows. The flux of reduced chemicals into the ocean from the crust declines, narrowing the range of environments where chemosynthetic communities can thrive. Microbial ecosystems that rely on strong chemical disequilibria become confined to fewer sites or must adapt to weaker gradients. The deep biosphere beneath the seafloor also feels this decline. Microorganisms living in pore spaces and fractures depend on heat-driven fluid circulation and on the slow release of chemical energy from rock-water interactions. As temperatures fall and circulation weakens, the metabolic rates of these communities drop, and the habitable volume within the crust contracts. In the upper ocean, changes in climate and atmospheric composition modify stratification, the layering of water by density. Warmer surface waters relative to the deep ocean create stronger density, contrasts that inhibit vertical mixing. Colder climates allow deeper convection in some regions but can lock away water in ice sheets and caps, reducing ocean volume. Over time, as external forcing shifts, circulation patterns can reorganize. Overturning currents may weaken or transform, and upwelling zones that bring nutrients to the surface may diminish. Nutrient inventories and ecosystems evolve as geological processes proceed. Weathering of continental rocks on planets with exposed land surfaces delivers dissolved ions to the ocean. As internal heat and tectonic activity decline, the rate at which fresh rock is brought to the surface slows, and long-term input of nutrients can fall. In the absence of strong recycling through subduction and volcanism, some nutrients become locked away in sediments. High-energy input and abundant nutrients can sustain complex food webs with large organisms and rapid turnover. As energy flows weaken and resupply slows, ecosystems reorganize towards simpler structures dominated by smaller, more efficient organisms that tolerate low resource conditions. Deep ocean communities that rely on sinking organic matter from the surface become more limited as surface production declines. Water inventories can also change. On planets subject to increasing stellar luminosity, evaporation from the surface may intensify. If atmospheric escape processes remove hydrogen derived from water at high altitudes, an irreversible net loss of water can occur. Over long periods, oceans can shrink, leaving smaller seas or isolated basins. As surface water retreats, the remaining oceans may become more saline and more stratified. Their capacity to host extensive, well-connected deep habitats diminishes. On colder worlds, water may instead become trapped in thick ice shells or glaciers, isolating liquid reservoirs beneath ice, but still allowing subsurface oceans to persist where internal heat is sufficient. Subsurface oceans, whether beneath ice shells on icy moons or within thick crusts on distant planets, depend strongly on interior heat. When radiogenic and tidal heating are strong, these hidden oceans can remain liquid and support circulation and chemistry at the ice-rock interface. As heat sources wane, ice shells thicken and convection in the interior slows. the rate of nutrient and energy transfer between rock, water, and any overlying ice declines. The volume of liquid water may contract, and parts of the deep biosphere that once access active interfaces become isolated in colder, more stagnant environments. Across the universe, the number of oceans in any given state at a particular time reflects the ages and sizes of the planets that host them and the luminosities of their stars. Early in cosmic history, many newly formed planets carry hot interiors and, where conditions allow, vigorous hydrothermal and volcanic activity beneath their oceans. Later, as the average planet becomes older and star formation slows, more oceans belong to worlds with reduced internal heat, altered climates, and less dynamic nutrient cycles. From this perspective, planetary oceans and their deep biospheres participate in the broader trend toward declining energy flows. Initially, they serve as active interfaces between space, rock, and interior, with strong gradients and rapid cycling. Over time, internal and external energy sources weaken or shift. Circulation patterns decelerate, and the range of environments that support high biological productivity narrows. Oceans still move, mix, and host life, but on many worlds they do so in ways that are gradually simpler and more constrained than in their earlier, more vigorous phases, reflecting the slow cooling of interiors and the evolving output of their stars. On the surfaces of rocky planets that carry air and water, land rises above oceans as continents and islands. Solid ground presents rough terrain to climate and life, with mountains, plains, basins, and plateaus shaped by tectonics, erosion, and deposition. On such land, sunlight falls directly on exposed rock and soil. Winds blow without the cushioning effect of deep water, and temperature swings between day and night or between seasons can be large. Where moisture is sufficient and conditions fall within suitable ranges, life spreads across this surface, building ecosystems that link atmosphere, crust, and shallow subsurface into a single dynamic system. On a planet like Earth, land ecosystems draw their main external energy from sunlight. Plants, algae in moist habitats, and photosynthetic microbes capture photons and convert part of their energy into chemical bonds through photosynthesis, producing organic matter and releasing oxygen or other byproducts. This primary production supports food webs of herbivores, predators, scavengers, and decomposers. Soils act as reservoirs and reactors, where fungi, bacteria, and small animals break down dead organic material, recycle nutrients, and influence the physical structure of the ground. Rivers, rain, and groundwater transport dissolved substances across landscapes, linking distant regions and moving material from high elevations toward coasts. These land systems do not remain fixed through time. Climate shifts, driven by changes in orbital configuration, greenhouse gas levels, continental positions, and stellar luminosity, alter temperature and precipitation patterns. Mountain ranges rise and erode, opening and closing pathways for migration. Sea levels advance and retreat, sometimes covering continental areas with shallow seas and then exposing them again. Life itself modifies the environment, as extensive plant cover stabilizes soils, affects albedo, and participates in the cycling of carbon between atmosphere and crust. Against this backdrop of physical change, lineages of organisms diversify, adapt, and go extinct. The fossil record preserves a partial chronicle of these changes. Layers of sedimentary rock contain remains and traces of past organisms, from simple impressions of leaves and shells to bones and footprints. By combining fossil data with radiometric dating and stratigraphic analysis, researchers reconstruct a history of diversity on land. This history shows long periods during which the number of species and the complexity of ecosystems increase, interrupted by episodes of elevated extinction. These episodes range from regional events tied to local environmental changes to global crises that remove a large fraction of species in a relatively short geological interval. Background extinction is a continuous process. Even in stable climates, species disappear as conditions shift slightly, competitors evolve, or random events translate into permanent loss. At the same time, new species arise through speciation, when populations diverge and adapt to different niches. Over millions of years, this balance between origination and extinction shapes the overall level of diversity. During favorable periods, origination exceeds extinction, and diversity rises. During stressful periods, extinction rates increase and diversity plateaus or falls. Mass extinctions represent more extreme departures from background rates. In these events, environmental stresses intensify on a global scale. Data from Earth indicates several such episodes, associated with combinations of factors such as large-scale volcanic eruptions, rapid climate warming or cooling, changes in ocean chemistry, and asteroid or comet impacts. On land, these stresses manifest as sharp shifts in temperature and rainfall, widespread wildfires, soil erosion, and the collapse of plant communities. Animal lineages that depend on particular habitats or narrow ranges of conditions often suffer high losses. After a mass extinction, surviving species expand into newly vacant ecological niches. This recovery phase involves both the spread of generalist organisms that tolerate a wide range of conditions and the gradual evolution of more specialized forms. Ecosystems rebuild structure, but they do so with a reduced set of lineages. Some entire branches of the tree of life disappear and do not reappear. The new communities that emerge may use energy and resources in different ways from their predecessors, reflecting both the altered environment and the narrower genetic base from which they arise. Over repeated cycles of expansion and crisis, the pattern that emerges is not a simple, smooth increase in richness. Instead, diversity on land fluctuates. Certain intervals show high levels of complexity, with intricate food webs and many specialized roles. Others show simplified systems dominated by a small number of robust lineages. In some cases, crises favor smaller, faster reproducing organisms over large, slow breeding ones. These survivors often share traits that allow them to endure low resource availability, high environmental variability, or both. In the long run, such traits can bias future ecosystems toward forms of life that use energy more sparingly or that occupy narrower, more stable niches. Energy flow through land ecosystems depends on the rate of primary production at the base of food webs. This rate in turn depends on the amount of sunlight reaching the surface, the availability of water and nutrients, and the efficiency with which plants and microbes convert light and raw materials into biomass. As planetary interiors cool and tectonic activity changes, weathering rates, volcanic gas emissions, and mountain building evolve. These processes influence nutrient delivery to soils and the long-term carbon cycle. As stellar luminosity slowly changes, the distribution of climate zones adjusts on long timescales. Such shifts alter where and how strongly land ecosystems can sustain high productivity. With time, soils tend to become more developed but also, in some contexts, more strongly leached of certain nutrients. Erosion and deposition redistribute materials, but in the absence of vigorous tectonic uplift and volcanism, the exposure of fresh, unweathered rock slows. This can reduce the long-term supply of some key elements to ecosystems. In response, plant and microbial communities evolve mechanisms to recycle nutrients more efficiently and to tolerate poorer soils. These adaptations allow continued function, but may also limit the maximum rates of productivity and reduce the range of conditions under which complex, energy-demanding organisms can thrive. The spatial arrangement of land habitats also shifts over geological intervals. Continental drift moves land masses across climate zones. Supercontinents assemble and break apart, altering coastlines and the proportion of land in equatorial versus polar regions. Extensive interior regions of large continents tend to experience more extreme seasonal climates and less maritime moderation, which can make conditions harsher for some forms of life. Fragmented continents with many coastlines offer more mild environments, but also depend on tectonic settings that change through time. As tectonics slows on aging planets, the frequency and scale of such rearrangements may decrease, leading to longer periods of relatively fixed continental configurations and associated climate patterns. On a cosmic scale, the detailed sequence of events on any one planet is unique, but certain general features repeat. Land ecosystems flourish when energy and nutrient flows are strong and climate remains within moderate ranges. They contract during intervals of rapid climate change, large volcanic outpourings, or space impacts, over very long spans. Internal and external energy sources trend downward or shift in ways that reduce the frequency of highly favorable conditions. Extinctions continue, recoveries proceed, but the envelope of possible climates and landscapes gradually changes. In this setting, the long-term tendency is toward land communities that function with lower energy throughput and that occupy limited environmental windows. High-diversity peaks, with many large and complex organisms engaged in intense energy use, become less common relative to periods dominated by smaller, more efficient, and often more generalist life forms. Fossil-bearing rocks on worlds like Earth record both the flourishing intervals and the losses, showing that the structure of land ecosystems responds sensitively to physical changes in planet and star. As the universe ages and more land surfaces spend more time under altered climates, reduced tectonic activity, and shifting atmospheric composition, the rise and fall of terrestrial diversity follows the broader trend towards systems that, while still alive, operate within narrower energetic and environmental bounds than before. Complex organisms in oceans, on land, and in the air use energy in more concentrated and structured ways than simple microbes. Multicellular bodies require coordinated transport of matter and energy to many cells at once. Nervous systems, muscles, and intricate behaviors depend on continuous flows of chemical energy. Food antioxidants provide this energy, and at each step conversions release heat to the surroundings. Complex organisms act as channels through which organized chemical gradients are turned into movement, growth, and then into diffuse warmth that spreads into air, water, and rock. In a food chain, primary producers capture energy from sunlight or chemical sources and store it in organic molecules. Herbivores eat these producers, carnivores feed on herbivores, and decomposers break down dead material. At each step only a fraction of energy passes upward. Most is dissipated as metabolic heat. High-level consumers therefore depend on wide bases of production beneath them. In ecosystems with many layers and branching food webs, the total energy throughput can be large even though only a small share reaches the top levels. Complex life tends to develop and persist where strong, steady energy sources are available. On planets with abundant sunlight and suitable air and water, dense photosynthetic communities can grow, and animal communities that consume plants and each other can flourish. Where hydrothermal systems are active, microbial mats and animals assemble around vents that release chemical energy from the interior. In such settings, organisms evolve specialized organs, symbioses, and behaviors that allow more complete use of available gradients. Greater efficiency in capturing usable work usually means faster local dissipation of those gradients. Over geological time, some lineages reorganize environments on large scales. Plants change the reflectivity of continents, influence evaporation and rainfall, and affect rock weathering. Burrowing animals mix soils and sediments, altering how oxygen and nutrients penetrate the ground. Large herbivores and predators shape vegetation structure and biomass distribution. These activities do not create energy. They rearrange matter and redirect existing flows, often increasing the rate at which stored chemical potential. Energy becomes heat, and dilute waste spread over wider regions. The rise of technological societies amplifies this role. On at least one planet, organisms with large brains and elaborate social structures learn to tap energy sources much more concentrated than typical biological fuels. Fire allows rapid use of plant matter. Later, these societies harness wind, flowing water, and fossil fuels, and eventually nuclear reactions. Fossil fuels are carbon-rich compounds built up from ancient biomass over hundreds of millions of years. When extracted and burned over short intervals, they release this stored energy quickly, along with gases and particles that spread through air and oceans. Technological energy use reshapes landscapes and seascapes. Forests are cleared, soils are ploughed, rivers are dammed, and coasts are engineered. Urban regions concentrate material and energy flows in dense, ordered arrangements of buildings, roads, and machines. These local increases in order require continuous input of energy and matter, drawn from much larger areas. Waste heat and byproducts disperse into the environment, increasing disorder and pushing systems toward more uniform distributions of energy and chemicals. Technological societies also speed up several natural processes. Weathering of rocks, which would proceed slowly under the action of rain and roots, is accelerated when rocks are mined, crushed, and exposed. Carbon that would remain locked in sediments or deep reservoirs is moved into the atmosphere. Nitrogen that would be fixed gradually by microbes and lightning is converted into reactive forms in industrial plants and added to soils. These actions alter biogeochemical cycles, increasing exchange rates between reservoirs and reducing long-term gradients built up over previous eras. Information processing consumes energy as well. Brains and artificial computing devices require continuous power to maintain ordered patterns of activity. Useful computations correspond to transitions toward more ordered internal states, but they are accompanied by the release of heat into the surroundings. As societies develop extensive communication networks and data systems, they devote a share of their energy budgets to these activities. Local decreases in informational entropy are balanced by increased entropy in the combined system of devices and environment. As the universe ages and the availability of high-quality energy sources changes, the options open to technological societies also change. The declining rate of star formation reduces the creation of new bright, short-lived stars and dense gas clouds. Over long periods, Accessible fossil fuels on any given planet are finite and, once burned, cannot be regenerated on comparable timescales. Nuclear fuels are also limited. Renewable sources such as sunlight, winds, and tides continue to deliver energy as long as stars shine and planetary rotations and orbits persist. But these flows respond to slow shifts in stellar output and planetary dynamics. On galactic scales, the average energy budget available per unit mass tends to decrease as fewer new stars form and as existing stars move into less luminous phases. Complex and technological life, where it appears, operates within energy landscapes set by this history. Early in a galaxy's life, strong gradients may be locally available but short-lived. Later, gradients are weaker but may persist for longer around stable, low-mass stars. Complex organisms and societies therefore participate in an ongoing process of energy redistribution rather than reversing it. They concentrate matter, build structures, and store information. Yet each of these actions draws on gradients established by earlier cosmic and planetary processes. The energy they use eventually leaves as heat, and the ordered materials they arrange tend, without continued maintenance, to decay or erode back toward less ordered states. Over time, the cumulative effect of life, particularly in its complex and technological forms, is to accelerate the conversion of concentrated energy and matter configurations into more diffuse, mixed, and less structured arrangements. From the standpoint of physics, this role fits within the broader direction of an evolving universe. Complex life can delay local equilibration, hold gradients in place for a time, or channel energy into particular pathways, but it does not halt the underlying trend toward the spread of energy and the smoothing of contrasts. As stars age, as planets cool, and as accessible energy reservoirs are drawn down, the scope for high energy, high complexity activity narrows. Living systems and their societies adjust, simplify, or disappear, while the larger scales on which they operate continue along trajectories set by cosmic initial conditions and by the irreversible nature of energy dissipation. At the smallest scales of ordinary matter, atoms and molecules move, collide, and interact in ways that follow statistical patterns. In a gas, molecules travel along straight paths until they meet others or strike surfaces, then bounce away in new directions. In a liquid, they slide past one another, jostling constantly. In a solid, atoms vibrate around fixed positions, exchanging energy through lattice vibrations. At any non-zero temperature, this motion never fully stops. Even in a seemingly still material, particles move, and these microscopic motions together determine the macroscopic properties of temperature, pressure, and phase. Temperature, in this description, measures the average kinetic energy of particles. At higher temperatures, molecules move faster, collisions are more energetic, and the distribution of speeds extends to higher values. At lower temperatures, speeds are slower, and the distribution narrows. Pressure in a gas arises from many impacts of molecules on container walls or on other boundaries. Diffusion, the spreading of a substance from regions of high concentration to low, occurs because random motions and collisions step particles into new positions, gradually smoothing out differences in density. Entropy is a statistical measure of how many microscopic arrangements correspond to a particular macroscopic state. Systems with strong gradients or ordered structures have relatively few microstates that match their large-scale appearance. Systems that are mixed and uniform have many more. When particles are free to move and interact, and when no external work is done to maintain specific patterns, the most probable evolution is towards states with higher entropy, where energy and matter are more evenly spread and where microscopic configurations are more numerous. This statistical tendency underlies the second law of thermodynamics. Chemical reactions follow similar principles. Reactants and products correspond to different arrangements of atoms and electrons, with distinct energies and numbers of available microstates. When molecules meet and react, they move along pathways that depend on energy barriers and on the distribution of kinetic energies. At a given temperature, some collisions carry enough energy and occur in suitable orientations to overcome barriers and form products. As reactions proceed, chemical potentials, measures of the free energy per particle, decrease as systems move toward equilibrium. At equilibrium, forward and reverse reactions occur at equal rates, and the composition becomes stable on average, reflecting a balance that maximizes entropy subject to constraints. Phase changes, such as melting, freezing, boiling, and condensation, also involve shifts in entropy. A crystalline solid has a regular ordered lattice. A liquid, with its disordered particle positions, has higher entropy at the same temperature. When a solid melts, it absorbs latent heat, energy that goes into increasing entropy rather than raising temperature. Similarly, when a liquid vaporizes, the gas phase that results has still higher entropy because molecules are free to occupy a much larger volume at fixed temperature and pressure. The equilibrium between phases reflects the balance between energetic costs of breaking interactions and entropic gains from increased disorder. In many contexts, gradients in temperature, concentration, or chemical potential are established by external processes. A heat source warms one region while another remains cooler. A reaction or separation sets up a difference in composition between two compartments. As long as these gradients exist, they can drive currents, heat flows from hot to cold, particles diffuse from high concentration to low, and reactions run spontaneously from higher to lower free energy. Over time, if no additional work is done, these currents weaken as the system approaches a uniform state in which temperatures, concentrations, and chemical potentials are equalized. Life and other complex structures rely on these gradients, but do not reverse the basic direction of spontaneous processes. A cell maintains ordered internal composition only by coupling reactions that build structure to reactions that dissipate energy. Nutrients with high free energy enter, waste products with lower free energy leave, and heat is transferred to the surroundings. The cell exists in a non-equilibrium steady state, with continuous turnover of molecules. If the external supply of high free energy molecules stops, internal processes run down, gradients across membranes flatten, ordered macromolecules degrade, and the system approaches equilibrium with its environment, a state of higher entropy for the combined system. Crystals, snowflakes, and other ordered structures can form spontaneously under suitable conditions, but their formation is driven by overall trends toward lower free energy and higher total entropy. When a liquid freezes, the local decrease in entropy inside the crystal is compensated by heat released to the surroundings, increasing the entropy of the environment by a greater amount. Similarly, when gases condense into droplets, latent heat is emitted, warming the surrounding air. Local order arises as part of a larger process in which the total number of accessible microstates for system plus environment grows. On cosmic scales, the same statistical principles apply. Radiation fields, made of photons, also have entropies that depend on their energy distributions. A hot source emits many high-energy photons, which can drive processes such as photochemistry and heating at great distances. As these photons travel and interact, they are absorbed and re-emitted, scattering to lower energies and more isotropic distributions. The cosmic microwave background, originally a high-temperature radiation field, cools and stretches with the expansion of space, moving toward a more dilute state with lower temperature but higher entropy per photon. Interstellar and intergalactic media provide larger-scale examples of diffusion and equilibration. Sharp differences in temperature or density generated by shocks, active galactic nuclei, or stellar winds gradually soften as heat conducts. Turbulence mixes gas, and radiation carries energy outward. Heavy elements produced in stars and released by supernova disperse into their surroundings, enriching wider volumes. Initially, these metals are concentrated in small regions, but over time they mix into more uniform distributions, raising the chemical entropy of the gas as compositional gradients fade. Gravitational systems behave in more complex ways because self-gravity can lead to local decreases in entropy as matter collapses into stars, planets, and compact objects. Yet even here, the process involves the release of energy. As gas falls inward, gravitational potential energy converts into heat and radiation. The forming object may become more ordered, with lower entropy per unit mass, but the emitted radiation increases the entropy of the environment by a larger amount. The combined entropy of matter and radiation still rises. The same holds for the collapse of massive stars into neutron stars or black holes, where enormous amounts of energy are radiated away in neutrinos and photons. At the level of individual particles, collisions and interactions gradually erase detailed information about initial conditions. Given enough time, a gas confined in a box approaches a Maxwellian distribution of velocities, regardless of the specific initial arrangement, as long as energy and particle number are conserved. In practice, external influences and boundaries limit how far this approach to equilibrium proceeds, but the underlying mathematical description shows that the most probable states, those with the greatest entropy, occupy the largest volume of phase space. Less probable, more ordered states require continuous work to sustain. As the universe ages, many of the processes that create strong gradients proceed more slowly or have already occurred. Star formation, which once produces intense radiation fields and fresh sites for chemical disequilibria, declines. Planetary interiors cool, reducing the supply of heat that can drive convection and geochemical cycles. The frequency of major shocks and violent mixing events in the intergalactic medium decreases as large-scale structure formation slows. The microscopic dynamics remain active, with particles moving and interacting, but the macroscopic patterns of these interactions increasingly reflect near equilibrium conditions rather than ongoing, large departures from them. In this sense, the direction of change at molecular and atomic scales aligns with the broader thermodynamic course of the universe. Matter and radiation rearrange themselves, passing from states with strong contrasts and low entropy towards states with weaker contrasts and higher entropy. Local systems can temporarily move against this trend by using external energy to build structure, but their activity relies on and contributes to the overall spread of energy. Over very long spans, as sources of free energy are used and as remaining gradients weaken, microscopic dynamics continue under constraints set by a cosmos that, on average, has fewer sharp differences in temperature, composition, and density than it once does, and more configurations in which energy is dispersed among many particles and many available microstates. In the far future, the universe continues to expand under the influence of dark energy. Galaxies that are not gravitationally bound drift farther apart at an accelerating pace. Within a typical large galaxy, distant systems redshift beyond detectability, leaving only a local remnant of the original group or cluster as the accessible cosmos. The cosmic microwave background cools further as its photons stretch to longer wavelengths. Its temperature falls ever closer to absolute zero, and its radiation becomes so dilute that it is effectively lost in the general darkness of space. Inside the remaining bound structures, stars follow their evolutionary paths to completion. The last reserves of cold gas are slowly converted into new stars or dispersed by stellar winds and outflows. Over immense spans of time, the rate of star formation falls towards zero. Eventually, the supply of gas that can cool and condense is exhausted or locked away in forms that do not readily collapse. Galaxies enter a stage where almost all luminous stars are survivors from earlier eras, and very few new stars ignite. The stellar population shifts toward a mix dominated by long-lived, low-mass stars and stellar remnants. Red dwarf stars, with main sequence lifetimes far longer than the current age of the universe, continue to burn hydrogen steadily, while more massive stars have already become white dwarfs, neutron stars, or black holes. Over times far exceeding any present epoch, even these low-mass stars deplete their core hydrogen and leave behind additional white dwarfs. The light output of a galaxy decreases steadily as the most luminous stars disappear, and the remaining stars emit at lower intensities and cooler temperatures. White dwarfs cool and fade as they radiate away their residual heat. In the distant future, they become so cold that they no longer emit substantial visible light, turning into dark, degenerate objects. Neutron stars slowly lose their rotation energy and magnetic activity, so their emission of high-energy particles and radiation declines. Black holes, containing matter within regions from which light cannot escape, persist as massive compact objects that influence their surroundings primarily through gravity. The large-scale distribution of matter in a cluster remnant becomes a population of faint stars, cold stellar remnants, planets, free-floating bodies, and black holes moving through an increasingly tenuous medium. Interactions and close encounters still occur, leading in rare cases to collisions or to the capture and accretion of material by compact objects. Over very long times, gravitational encounters transfer energy between orbits, causing some bodies to gain enough velocity to escape the system, while others fall inward. Mass is gradually redistributed, concentrating material into central black holes and ejecting lighter components into intergalactic space. On even longer timescales, processes that are negligible in the current epoch may become important. Some theoretical models suggest that protons, the building blocks of atomic nuclei, may decay over extremely long half-lives. If proton decay occurs, bound matter in baryonic form would slowly transform into lighter particles, reducing the amount of stable atomic matter. Experiments have not yet detected proton decay, so its occurrence and rate remain uncertain. If protons are stable, atoms and molecules composed of them could persist far longer, altering details but not the overall direction of cosmic evolution. Black holes are predicted by quantum field theory in curved spacetime to emit a faint thermal radiation, a process often called Hawking radiation. This radiation causes black holes to lose mass over time. For stellar mass and larger black holes, the timescales for significant evaporation are extremely long compared with the present age of the universe. Nevertheless, in descriptions that extend indefinitely forward in time, this process leads to gradual evaporation, As black holes lose mass, they become hotter and radiate more strongly, ending in final phases that release their remaining energy into surrounding space as particles and radiation. Whether or not proton decay occurs, and regardless of the detailed particle content of the far future universe, the general trend is that concentrated energy sources become rarer and less powerful. Nuclear fusion in stars ceases when fuel is exhausted. Residual thermal energy in stellar remnants and planets radiates away. If black holes evaporate, their mass energy ultimately becomes a bath of low-energy particles and radiation. The expansion of the universe continues to stretch this radiation to longer wavelengths and lower energies, further diluting it. As structures exhaust their internal free energy, the ability of remaining processes to create and maintain large-scale gradients diminishes. Chemical reactions that depend on strong differences in temperature or chemical potential become rare or proceed only slowly. Mechanical motions on large scales either settle through dynamical relaxation or persist without generating new disequilibria. Matter spreads out or remains confined in compact remnants that interact weakly with one another. The universe does not reach a perfectly uniform state, but the contrasts that remain carry little usable free energy. In many treatments of cosmic evolution, this asymptotic state is described as heat death. The term refers not to high temperatures, but to a condition in which energy is so uniformly distributed that no macroscopic work can be extracted from it. In such a state, processes of structure formation or complex dynamics are limited to rare fluctuations and to small scales. The overwhelming majority of matter and radiation resides in configurations close to thermodynamic equilibrium, with near maximal entropy given the constraints set by conserved quantities. The precise details of this ultimate fate depend on physical laws that are still being refined and on the long-term behavior of dark energy, which is not yet fully known. Different scenarios lead to variations in how quickly horizons expand and how structures detach from one another. However, within the currently favored framework, in which dark energy behaves similarly to a cosmological constant, and the universe continues to expand without bound. The common feature of far future models is a steady reduction in accessible free energy and in the formation of new, luminous structures in the limit of long times. The cosmos becomes dominated by dark, cold remnants and diffuse, low-temperature radiation. Bound systems remain, but their internal activity is minimal. Particles and photons still move and interact, yet they do so within an environment where gradients are weak and where most states correspond to configurations near equilibrium. The universe that results is not empty, but it is quiet, with little capacity to support complex energy-intensive phenomena.